Hello everyone, let's talk about the periodic trends. These are the four trends that we are going to be talking about. You can feel free to skip to the ones that I asked you to work on today. Just a quick thing to note down, please copy this down in your notes packet. When we talk about the periodic trends, we only observe these trends in groups 1, 2, and then group 13 to 18. We call these groups the representative elements because they represent the periodic trends. The transition metals that we see from group 3 to 12, they do not quite have these periodic trends. So let's begin our discussion with the atomic radius. This is on page 7 in your notes packet. Pause the video, take a few seconds to think about what you know about the atomic radius. So atomic radius is the distance from the center of the nucleus to the outermost shell or the valence shell. Or in other words, we can also say it's the distance from the center of the nucleus to the valence electrons. That's the same thing. Now pause the video again and take a few moments to think about it. You definitely don't have a neighbor to talk to, but just think about what trend do you think you will observe as we go down the group from top to bottom and across the period from left to right in the periodic table. So whatever your answer is, that would be your prediction. And here's the actual trend for atomic radius. As we go down the group in the periodic table, atomic radius generally increases, and as we go across the period from left to right in the periodic table, atomic radius decreases. So let's talk about how that happens or why that happens. Now pause your video again, and in this part of your notes packet, draw the Bohr diagram in that bigger box for each element that's given, and then right next to the symbol for the element, write the atomic radius. So think about where can we find the atomic radius. It should be given in table S. Please do not forget your units. Here's what your final diagram should look like with the atomic radius that you copy down from table S. If you observe, as we are going across the period from beryllium to fluorine, atomic radius is decreasing, just like we said in the trend. And as we are going down from beryllium to calcium down the group, the atomic radius is increasing. So then this next set of questions with these diagrams is asking you to try to explain why is that happening, or what are some of the things that we observe in these diagrams that kind of explain these trends. So take a moment, pause the video, think about these answers. So what happens is that as we go down the group in the periodic table from top to bottom, every time we go to a new element in a group, we are adding an energy level or an orbit. So that is what causes an increase in the atomic radius as we go down the group. However, as we are going across the period, we still have same number of orbits. So what's changing is the number of protons because the atomic number is increasing. And now remember, in the neutral atom, the number of protons is equal to the number of electrons. So because we have more protons, we also have more electrons. So the number of valence electrons are increasing. So those more protons in the nucleus and more valence electrons, they are getting attracted to each other because we have more, we are increasing their number, but they're still living in the same amount of space. So that attraction between the protons in the nucleus and the valence electrons is what we call the Coulombic attraction. And because of this attraction, the atom shrinks, which is why the atomic radius decreases. Now, let's pause the video again and take a moment to think about the ionic radius. So the concept of radius is still the same. It's the distance from the center to the circumference, but in this case, we are looking at the distance between the center of the nucleus and the valence electrons in an ion instead of just an atom like we were doing in atomic radius. Now pause the video, and in this section, you are going to observe the two different types of ions that sodium and chlorine are going to make. And why are they making those ions? And what trends do you observe in their sizes? So we are looking at the size of the ion and we are comparing that size with the size of the atom. So what do you think about the size of the sodium ion compared to sodium atom? So what happens here is that sodium is making a cation, which is a positive ion, because sodium, remember, is a metal, and as we discussed, metals generally lose electrons. Also, sodium only has one valence electron, so it's easier for sodium to lose that one electron rather than gaining seven to have a complete octet. And because sodium is losing that electron, it's going to be smaller in size compared to the sodium atom. Chlorine, on the other hand, is gaining one electron because right now it has seven valence electrons, so it's easier for chlorine to gain one electron and have a complete octet. Also, chlorine is a nonmetal, and nonmetals generally gain electrons. So that is going to the anion is going to have be bigger, larger in size compared to the chlorine atom. So now in that box that you see, let's write down the trend. So we said that metals form cations, which means they generally lose electrons. And cations, as we lose an electron, we are also losing the outermost shell, which is why cations are smaller than the actual atoms. Nonmetals, however, generally gain electrons, so they make anions. And because as they are gaining the electrons, but we still have the same number of protons in the nucleus, so there's less attraction towards the nucleus, and there's more repulsion between those like extra electrons. So that's why the anions are larger in size compared to the atoms. Now let's jump to page 8 in your notes packet where we have the ionization energy. Take a moment to think about these 4 questions. Write down your answers. We'll discuss them when we come back together in class. So here we are going to be talking about which elements are the most reactive. So take a moment, pause the video, think about what do you think ionization energy is? So this is the energy required to remove an electron from the valence shell of an atom, because this is the first step for any atom to go ahead and react. So if there's a lot of energy that's required to remove an electron from an atom, that atom is most likely not going to be so reactive. Pause the video again, draw the Bohr diagrams, and complete the required information for all of these elements. This is what your final result is going to look like with the Bohr diagrams and with all the asked information. So now based on your diagrams that you just made, in this part of your page, let's first make a prediction about the trend that you observe in the ionization energy as we go down the group and across the period in the periodic table. Now let's write down the real trend and some explanations for why do we observe that trend. So as we go down the group in the periodic table, ionization energy decreases, which means less energy is required to remove an electron from the valence orbit of an atom. And that's because as we go down the group, the atomic radius is increasing, the atoms are becoming bigger and bigger, and we have more shielding electrons, which means there are more electrons between the nucleus and the valence orbit. So the more electrons there are, the less attraction the nucleus has on the valence orbits, which is why it's going to be easier for us to remove an electron from the outermost shell. Comparatively, we said that across the period, the atomic radius decreases because there's more pull, there's more attraction towards between the nucleus and the valence electrons. So in that case, it's going to be harder for us to remove the electrons from the outermost orbit, which is why the ionization energy will increase because we need more energy to remove an electron from the valence orbit. Now at the bottom of your page, we do have a little space on page 8. So let's write down this question. Why do we think that group 1 metals are the most reactive? So pause the video and think about your answer. Your answer should be that because the group 1 metals have least ionization energy, which means we need the least amount of energy to remove an electron from their outermost orbit, so it's easier for them to lose electrons, make those ions, and then go ahead and react, which is why they are the most reactive. Now let's jump to page 9 in your notes packet. Um, take a moment to think about the answers to these two questions. We'll discuss them when we come to class. Now pause the video again and think about which element do we think in group 17 is the most reactive, and then also write down your reason for that. Now, we did discuss this a little while ago in class that fluorine is the most reactive in group 17. Uh, now, some of you, if you didn't recall that, some of you might have said that the elements at the bottom of group 17 are the most reactive based on what we just learned about ionization energy, because the elements at the bottom of group 17 have the least ionization energy, so you might have thought that it's easier for them to lose electrons, so they are going to be most reactive. However, there's another phenomena that also plays a huge role in determining the reactivity, and that is the electronegativity. So the atoms at the top of group 17 have more ability to attract the electrons of other atoms, and that is also something that's very important for an atom to react. So that's technically our aim for today, that why fluorine is the most reactive nonmetal. So electronegativity is just that ability of any atom to attract the electrons of other atoms, and it's a relative number. It goes from 0 to 4.0. Fluorine has an electronegativity of 4.0, and that is considered the most electronegative element in the periodic table. Now let's pause your video here and draw the Bohr diagrams and copy down the electronegativities for these elements. Remember, electronegativities are also given in table S, just like atomic radius and ionization energy. This is technically what your end product will look like. Of course, with bromine and iodine, I just got lazy, so I don't have those in there. You should have all of them. Now let's look at the questions on the side. So let's first look at that prediction part. Pause the video and predict why do we think fluorine is so reactive. Your answer should be somewhere along the lines of, because fluorine is a nonmetal and it's easier for nonmetals to gain electrons, which means in order to gain those electrons, they have to attract the electrons from any other atom. So fluorine is very electronegative. It can gain electron. It can attract electrons from other atoms. That's why it's so reactive. Now, in the next question over here, let's pause the video and let's think about why do we think it is easier for nonmetals to attract the electrons from other atoms, or why do they want to gain electrons? Why is it so easy for them? And remember, this is an in terms of question, so make sure your answer is mentioning the nuclear attraction. So what happens is that if you look at the nonmetals, and as we are, let's say if you're observing nonmetals in the same period, they have the same number of orbits, and they also have same number of electrons in their like completely filled orbits. Um, but because they're increasing the number of valence electrons and they're also increasing the number of protons in the nucleus, there's a higher Coulombic attraction between the protons in the nucleus and the valence electrons. So there's just in general a lot of attraction from the nucleus. And that attraction is so much that it's not just for the valence electrons, it can also attract the electrons from other atoms surrounding that specific atom. So now let's talk about the periodic trend for electronegativity. So what happens is that as we go down the group, the electronegativity decreases because we are increasing the atomic radius. There's not a lot of attraction from the nucleus. So the nucleus is already struggling so much to keep its own electrons like within their orbits, because those electrons are just so easy to be lost. Which is why as we go down the group, there's less nuclear attraction, which is why there's less electronegativity. However, as we go across the period, because there is a lot of attraction from the nucleus, because we are adding more protons, while keeping the same number of orbits, um, that increased nuclear attraction is what increases electronegativity, because the atom in general can attract the electrons from other atoms. Finally, towards the bottom of this page, you have two more questions. Please think about these answers, and we'll discuss them when we come back together. Now let's jump to page 10 in your notes packet, where we are going to be talking about the metallic character. Answer these two questions. We'll go over them whenever we are together. In the next section, we are going to be comparing the ionization energy and the electronegativity of metals and nonmetals, and then explain our answer. So in the lines that you see before ionization energy and electronegativity, explain using the arrows what if we compare the ionization energy of metals to nonmetals, then metals generally have a higher ionization energy or lower ionization energy, and then also explain your answers. Pause the video and think about this. So compared to nonmetals, metals generally have a lower ionization energy, which means we need less energy to remove an electron from the valence orbits of metals. And that's because nonmetals have a lot of nuclear attraction compared to metals. Metals also have a lower electronegativity compared to nonmetals, and that's because metals in general lose electrons. It's very hard for them to attract electrons from other things, which is why they have a lower electronegativity compared to nonmetals. So the aim for this lesson is just to see that if you're given a substance, how can we observe how metal-like that specific substance can behave. So metallic character is generally just a set of properties uh, that metals have. So if again we are given a substance, we look at the different properties, and that's how we identify how much of a metal that substance is. Now, next up, pause the video and think about this question. Why does it make sense that metals generally have, we said they have a lower ionization energy and lower electronegativity compared to nonmetals? So, you can have certainly different types of answers, but in general, your answer should be like something along the lines of metals want to like form cations. So it's because they want to lose their electrons to have the complete octet. And it's very hard for them to gain electrons. Now in this section, we are going to determine the periodic trend or for metallic character as we go down the group and across the period in the periodic table. So we discussed already that as we go down the group, ionization energy decreases because we have more orbits. There's less attraction between nucleus and the outermost orbit, so it's easier to remove electrons. We don't need a lot of energy to do that. And electronegativity also decreases because there's less attraction, so it's very hard for the nucleus to pull the electrons from other atoms. So these two, both of these things are pointing towards something that is more metal-like, because for an atom that has less ionization energy, it has less electronegativity, it doesn't want to pull electrons from other things, and it is really ready to lose its own electrons. That thing is very metal-like. So the metallic character actually increases as we go down the group. And that's because it is easier for electrons to, it's easier for the atoms to lose electrons. Comparatively, we said that as we go across the period, the ionization energy increases because now we have more attraction between the nucleus and the outermost electrons. So we really need a lot of energy to remove an electron from the outermost shell. And there's more electronegativity because again, there's more nuclear attraction. So the nucleus, it's very easy for the nucleus to pull electrons from other atoms as well. So both of these things are pointing towards something that is not so much metal-like, because remember, metals tend to lose electrons. In this case, it's very hard to lose electrons. So the metallic character is going to decrease as we go across the period, um, just for because of the fact that it's harder to lose electrons. So here's the general trend. As we go down the graph, metallic character increases, and as we go across the period, metallic character decreases. So that's it for the periodic trends. I'll see you guys in the next one.